Okay, so I'm Pranav. I'm a PhD student over here under the supervision of Xavier Carreras and Ariadna Quatoni. This is a joint work which I did when I was visiting Toyota Technological University at Chicago. So the thing that we're going to see is how can we map between two spaces and is it useful or not. So the title is Mapping Unseen Words to Task-Trained Embedding Spaces. So I'll just dive right in. So this is, let's consider a simple example for syntactic parsing. Now if we have, so these are the kinds of sentences that we get generally in day-to-day sort of media. So you have small birds make clamorous tweets. Since most of the NLP, so we have a corpora which is dated, so we may not have these words. And this is generally a problem in natural language processing and related fields, where you'll always have objects which you wouldn't have encountered in the training specifically when you're doing a supervised sort of model. So if you sort of have a supervised neural network, since this paper is sort of more oriented towards neural network, you can consider any kind of machine learning framework. If you have a supervised machine learning framework, it uses and updates words or lexical informations, then it's always possible that there are unseen words. Over here the unseen words are clamorous and tweets. Now if we don't have lexical information for these two, then we wouldn't have any information so as to sort of get these dependencies correctly, which is a sort of a problem in most of the natural language processing tasks, the lexical sort of deficiencies. So let's take another example. So here it's adjective noun. So we are just interested in just getting these adjective noun relations correctly. So vinyl can be applied to electronic devices and cases. Now consider a case where you have not seen electronic devices and cases. So if we have not seen electronic devices and cases, then the chances are we do not know if electronic is modifying devices, if electronic is modifying cases, if electronic is modifying devices and cases, or does either of them sort of modify, etc. So this is the lexical problem that we have. Even if you have complicated inferences in the final part, even then if you don't have information related to all these three objects, you wouldn't be able to sort of solve these kinds of probabilistic scores. So this is very common. It can be explained using Zipf distribution because most of the natural language processing words and lexical distributions follow a Zipfian distribution. So you'll have a small proportion of words that are most frequently occurring and a very small proportion of words which are not occurring frequently, and you do not have enough information or you don't know what to do with that. So generalization in general is a problem in most of the NLP models. So these days, most of the people have been, very excited about distributional word space models, which has been existing for a long period of time. So basically, distributional word space models use a hypothesis, which is the distributional hypothesis. It just states that if we have a particular word like moon, and we are interested in seeing what are the close by words, what are the surrounding words. So and then we take a couple of candidates. So this is how it works. So this is just in 2 dimensions. So I'm just saying here, in this case, we are just taking the frequentist analysis. So we are just saying, okay, so moon occurs. So if we are comparing 3 words and we have 2 of the surrounding words, shine and shadow, and we have dog, moon, and sun, and we see dog frequently, occurring with shine but not occurring with shadow, moon occurring with shine and shadow n number of times, and sun occurring with shine and shadow n number of times, then we can get some interpretation of it. We can get some kind of distributional information. We can get an angular information over here, and we can get a similarity measure. So we can say sun and moon are similar because they occur in similar contexts. But dog apparently doesn't occur in the similar context as sun and moon, and that's all we are making over here. That's the information. So generally people are working on this, and they have you know, there are better and newer methods which actually do a similar kind of thing. So the newer methods, the word embedding style methods, what they do, instead of explicitly saying these are the context words, they are actually predicting what are the context words and so forth, and they are getting these particular vectors. So these are word vectors, so they are n-dimensional vectors for each word. These contain several kinds of information. One of the information that people say are the so-called similarity informations. So these embeddings are generally used these days in modeling frameworks, especially for natural language processing tasks like parsing. So you initialize the input layer, you have the words, and you just initialize the words using these embeddings. These are word embeddings. So if you have has, good, control, so you'll have has, good, and control. You'll have the embedding sort of pushed in, and then you have a hidden layer, which is, since it's a neural network, we have a hidden layer over here, a single. So this is a typical example where we are using a single layer, hidden layer, and then we have an output layer which gives us the probabilistic distribution for particular task of, say, parsing. So it gives probabilistic distributions of what are the correct, parsing edges. So we are actually considering this kind of this kind of model. So we want a model which is initialized with word embeddings. But in neural networks, if you want to get all the compositionality in all the layers, then you have to back propagate and extract the compositionality, because what you're doing over here is you're just concatenating all the embeddings. So you're concatenating, you have the errors over here in the loss, and then you back propagate all the errors, update them. So generally what is happening is that, oops, again, I'm sorry. So generally what is happening is so initially you're starting with some embeddings, but the embeddings get updated. That means they are specified for that particular task. So initially, say your moon and sun are close together, but the task requires moon and sun to have a different property. Then what happens when you backpropagate is you're updating the embeddings and you're pushing them into a different space. So in essence, you're updating the embedding such that it performs well for a particular task. That's the essential property that we are focusing on. So
we do this in the second layer.
So generally what happens is, so here the loss is, say I want a parsing loss. Okay, so I have a parsing loss, a structure prediction loss in the top. I get the error and I backpropagate the error to the first layer as well as the last layer, the initial layer. So I backpropagate to all the layers.
That's the weights.
Yes. No, I modify the embeddings too. Right, I'm modifying the inputs too. Yeah. So I have the embeddings, initial embeddings, but then I'm updating the weights over here. I'm updating the weights, but I'm backpropagating the weights and the initial layer. These are also considered, you can see them as weights. Yes, you can see them as weights. One way to actually look at it is you can have all these words. Right. So you can just have indicator vectors, and each indicator vector corresponds to a certain vector, which is sort of a weight vector. You can consider that. But what essentially you're doing is you're backpropagating and updating each layer. So you're updating the initial embeddings too. So initial information is actually updated such that it is specific to that particular task. So one of the things is so even if you have embeddings in your hand, for words that you have not seen during training, you cannot use them now because the words that are there in this particular layer has been updated, right? So they have been updated and so the spaces are different now. That's the crux of the problem that we are actually looking at. So again, let's go back to the same example. Small birds make clamorous tweets. So supervision contains V, which is a subset of capital V, which is the whole vocabulary, which is a very small vocabulary. That's what you have in your supervision. So the problem that we were just discussing, the embeddings have been actually updated, so they are in a different space now. So the initial embedding space and the final embedding space, the model trained embedding space, are both in different spaces. Okay, so the thing is, since we are using a non-linearity in the neural network, suppose you have n layers, you have non-linearities over there, there is a chance that there are lots of linear and non-linear transformations which are happening in the space. So it's not easy to sort of say that, you know, doing X transformations on the initial thing will transport us to the other space. So that's the gist of the problem that we have. So what do we do with the unknown words? So what is being done right now for the unknown words is people use a default vector. They say, okay, let's use a default embedding for any unknown words. We'll just use that default embedding. So let it be a verb, let it be a noun, let it be anything. In most of the neural network based models, people use a default for anything that has not been seen during the training. So what generally happens because of that is you always encounter words which may have a completely different property, but then since you are giving the same information, you'll have errors. And that's propagating, and you'll have, suppose you're doing a structured prediction, then you'll have errors propagated and you'll have a completely faulty sentence parse. So what is generally done, as I was saying, so in Chen and Manning, the standard parsing, in others, in the latest Google work too, they use a single unknown word vector. Or what they can do is, instead of using a single unknown word vector, they can say, what are the rare words that we have encountered during training? Let's average them and let's approximate them as a single unknown word vector. And then suppose we encounter a new unknown word that we have not seen during training, we'll use this information for the model. So the model parameters are the same. We cannot change that, but the embeddings are information, but they have also been updated. So people are using some kind of a hack, which is, you know, use some kind of pre-trained embeddings. So you have the initial embeddings, initial information, also add some kind of unknown vector information, merge them somehow, and then let's pass them. So this is another work. So in general, the other neat tricks that people have applied is use character level embeddings, which, so Martha's work is basically using character level. So instead of going word level, let's go character level. So in that case, the vocabulary is constant for all languages. You have a particular vocabulary, so you can get character level embeddings. But one of the problems with character level embeddings is that it is too fine grained, and maybe you might be adding some noise, especially for tasks like parsing, where you probably need much more. The abstractness may not be as abstract as the character level might be giving. Maybe we need better abstraction, etc. So you might go there, or character level also produces words which may not be correct. So you might have words which are wrong, but it has produced a word which, because the morphological splitting, it might not be correct for every other sort of word. So it might be good for some words, it may not be good for other words. So the other people, what they do is they do a specific morphological splitting, and they add these morphological splitting information for these unknown words. They say, this particular word has these kinds of morphology, so because of these morphological information, we can say these are similar to some words. Some others use n-gram based information in the sense, okay, so you have n-gram based information from a large corpus, let's extract those information, let's say these words are similar to these words in the supervised training, let's use these kinds of information. The other work recently with the RNN based work, because recurrent neural network based work, what they're using is unknown token, which is learned as separately. So you learn it separately beforehand, and that's like it's an averaging for words below a threshold, plus you learn during training. It's like a pre-training step. And then there are hybrid steps, which is sort of a pre-trained plus task trained plus all these other information sort of merged together, and you give the information such that the model can probably take it and do something. So essentially we're focusing on this problem, that is, so lexical embeddings are easy to obtain because you have a large corpus in approximately all languages. online. These days it's available, all other media sources. You have basically a large corpus, you can get a lexical embedding. Now, we are not specifying which lexical embedding is better, etc. You just get a lexical embedding. And then the problem is the parser has updated the embedding for that particular task by backpropagating the errors. So this is our major concern. So basically the unseen words might potentially have discriminatory information which is required for the model, but we are unable to pass it to the model. So the parser either uses zero vector or some kind of default word embedding for all these kinds of unseen words. So that's one major issue that we are focusing on. The other thing is, if the parser has seen a particular word, any parser or any kind of model has seen a particular word for say 5 times or less, then you really don't know if you are able to generalize that particular word's specificity for that particular task as nicely as possible or not. So that's one major problem. That is overfitting of rarely observed words. This generally happens in supervised parsing or supervised neural modeling cases. So if the words have been observed during less than n times, can we sort of fix that? These are the questions that we try to ask. Oops, again, I'm sorry. So we started with this. So we asked the question, can we translate word embeddings? Can we translate word embedding spaces? Can we translate from space A to space B? So it seemed like there was some work which was saying that translations were possible. But again, we are doing a lot of nonlinearities, so are we easily able to translate? So most of the work which were there were targeting a linear transformation. So you multiply, you have a supervision on a very small corpus, and you have a linear sort of transformation. You take a word vector, linearly transform it such that it is similar to the other, to the task-trained vector. There also was a work which came in 2013, which is, do deep nets really need to be deep? This is by Ba and Caruana. So Rich Caruana has a lot of work. What he does is model compression. So he takes huge and deep models, and then so this is a teacher model, and then he builds a very small neural network or any other kind of supervised model which actually tries to replicate this deep model. So that's like a model compression. That's what is happening in most of your phones. So when you use Google Now or all these kinds of things, you probably have a very small offline model, which is actually a compressed model of a very deep sort of network, and you actually replicate it. It's known as a student-teacher network. And what he says is most of these nonlinear transformations which are happening can be captured in a very small model with essentially a very small set of parameters. So that means the parametric space is very small, but you're actually replicating this whole large nonlinearity which are existing in your model to a very small model. So this seemed possible. So that gave us the motivation to study why can't we do the same thing for translation of spaces. So we are targeting this particular concept of learning transformational spaces, space transformation from one space to another space. So in parallel, when we were doing our work, there were some work which were trying to see a similar problem and suggest solutions. So one of them was nearest neighbor in both spaces. So they are asking, can we sort of say that some nearest neighbors in space A and some nearest neighbors in space B, if they are same, then we can sort of have a metric which will actually try to translate using this nearest neighbors logic to another space. We actually compare. The other one is linear transformational space. So what they are doing is they are actually taking, they are learning a linear transformational function which maps from initial to a linearly transformed space, which is similar or close to the space that you want to replicate. So our proposal is we develop, again, a neural network, a single layer neural network based mapper, which maps from initial embedding space to the task trained embedding space. So for this, we actually propose a weighted multiple loss criterion. So instead of having a single loss, we say a single loss is sort of saying a Euclidean space. So you say, let me do an L2 loss, or let me do an L1 loss, or let me do some other kind of logistic loss, or something else. So instead of that, we propose a weighted multi-loss. So we have a Euclidean plus L1. So in the sense, what we want to say is our spaces may be similar in the Euclidean space or in the L1 space, but we really are not sure. So let's weight it and let the sort of let the supervised training take care of what is the correct loss for this particular thing. So the architecture allows us to have some control over kind of different domains. So if you have different domains and you have a model, so you have a parsing model and you have the model parameters already built in, you don't want to change the model because you have a very small tuning set, so you cannot do much. So what you can do is, let's keep the model parameters constant. Let's change the initial embeddings such that they are better performing than the original space. So that's what we do. We tune the mapper's hyperparameters, which I'm going to describe now, to optimize the performance on each domain. So what we are doing is, we are not just trying to learn to map the embeddings from one space to another, but we are also trying to fortify the mapped spaces. In the sense, if you have seen the words less than 5 times and you're not sure in the original space itself we have gotten the best kind of performance. So can we sort of improve that? So overfitted words, embedding spaces, can we sort of modify and sort of fit such that it performs well for our task? Sorry. So the basic architecture is, it's a single layer neural network with a hard tan H nonlinearity. Why hard tan H? Because we found that most of the others were also performing the same, and this is almost like this was easier for us to sort of implement. And we use a multiple loss criterion. So this is a multiple loss criteria. So you have the L1, this is the L2. So this is the L1 loss and this is the L2 loss. And then we use an elastic net regularization, which again tries to sort of regularize the space, both L1 as well as L2. So that's the basics of the model. So the training pipeline looks something like this. So basically, this is the parser model. So I'm not discussing about the parser training right now, because you can remove this model and put any of the other sort of model for any other task. So essentially, you have some model which takes in annotated training sentences as it is for supervision. It takes in initial embeddings, and we need initial embeddings. So because initial embeddings are learned using an unsupervised corpora, so it's easy to get, so we take the initial embeddings. So the initial embeddings are taken by the parser. The parser learns the model parameters as well as it updates the task-trained embeddings. So it updates the embeddings to task-trained spaces, to the task-specific case. So it has updated. What we do is we take this as the supervision, and we take the initial embedding as it is, and we are basically trying to minimize the loss between these two spaces, basically, embedding spaces. So we are actually minimizing the loss, and the loss that I mentioned just before, the loss was the L2 plus L1 loss. A weighted L2 plus L1 loss. So when you have done that, when you have gotten these, so when you have gotten these, then we can use the same thing to get the to get the mapped embeddings, to get the unseen vectors into the embedding spaces which the parser can take in. So this is the parser trained model, which is already the model parameters are fixed. The only thing that we are changing is the embedding spaces. Now we have mapped all the unseen words into the embedding spaces, so we have sort of given the information that the model has, that the parser has not seen. And we just do the parsing like that.
But basically what you're doing is adding a layer.
No, we are doing externally.
Yeah, you're doing externally.
Yeah.
It's an extra layer that makes this unequal.
Yeah, you can say that. Yes, yes, we are adding extra layer. Yes.
If you train it all together, you need to train it separately.
Yeah, we need to train it separately. I'll tell you why. So one of the reasons is here are the thresholds. So we actually put a threshold. So in the mapper training, so what you can do is you can control the kinds of words that you're giving. So you can say that I'll only give the words which have been trained properly, right? Which have occurred at least n number of times. That means I think that these words have been at least seen and updated such that, you know, the parser is doing essentially what it has to do. But for words which are seen once or twice, parser still updates because it's doing an average update. So now these words are actually containing information which may not be absolutely relevant for our task, right? I mean, yeah, it has been updated, but now it may not perform very well. So maybe we can actually update those words such that, you know, they are performing as better as, you know, as good as the words that have occurred n number of times. That's one problem that we encounter. So we also tried that. So what we did is we had a linear layer. So instead of projecting directly, can we do this? Sort of, you know, you project it to a layer and then sort of. So we did that, but we found that this was much better in capturing all these, you know, rarely occurring sort of words. So that's why we have mapper training. So that means only train the mapper on the words that occur n number of times, only those words. The other thing is mapping threshold. That means map the parse trained embeddings that appear less than n times. And then you have the parser threshold. That means the parser itself, during parsing, it uses the embeddings which have occurred, you know, greater than n times. So this is the feature that we get by doing an external sort of. So the internals of the sort of the mapper itself is that we are using LBFGS to sort of optimize. Alpha and lambdas are tuned using held out domain specific data. So the problem with dependency parser, well, mostly other fields also in NLP, is that you have a strong training set in the news domain, say, but you have a very small, you know, data set which has been parsed or which has been annotated by people, with like 1,000 sentences at max, but the training that you have done is on a completely different data set, which uses almost 50,000 sentences. Now, if you add these 1,000 to the training set, it doesn't make any difference because those are not, you know, the information content is very less, so the parser is unable to generalize. So that's why what we do is we sort of tune the parser using that, but the mapper is also tuned on that particular domain. So the mapper can actually say that, you know, so for words which have occurred n number of times less than, you know, a particular in the training set, then we can actually map it again. So the internals, again, dimensionality of the nonlinear layer is set to 400. So we take the 100 dimensional to 400 dimensional, and then we again reduce it to 100 dimensional representation. So the hyperparameters sort of give us an additional flexibility to map the embeddings for the domain of interest. So for experiments, we took the standard dependency parser from Stanford, which is Chen and Manning's parser, and then we used the word embeddings, which were 100-dimensional glove embeddings. You can use any kind of word vectors, any kind of embeddings. The data was the Wall Street Journal post. This is the training data, the Wall Street Journal of the Pentry Bank, so standard splits. For testing, we tried WebTree Bank, which contains data from Twitter, from social media, from blogs, from websites, from news, etc., from answers, etc. And for the downstream task, we also used this and then passed the mapped results to a sentiment analysis task, which uses an RNN-based network. So it uses dependency trees, dependency information to, you know, classify sentiments. So say, you know, this is happy, this is sad, this is angry, etc. So to just see what is happening, so this is the baseline parser, and this is our parser. So this is the mapped embedding. So the only thing that we are doing is we are just mapping the embeddings, and by just doing that, we get a decent boost. Now, one of the things is, if you notice, the boost is smaller in comparison to the boost over here, where we have approximately 1.5 percentage boost, and that's because in these cases the number of unknown words that were there in the Wall Street Journal set is very small. But in the other cases, when you go to other domains, like completely different domains like Twitter, etc., the number of unknowns keep increasing. And since we are able to map them, so here we have 2% sort of gains, etc. So as we map them, we get a significant boost. So so we also have so here what we have is we have the fine-grained classification. So we have so this is the fine-grained classification in the sense you're saying. So you have the levels of happiness, levels of sadness. So we see that fine-grained classification, given our mapped sort of dependencies, performs much better than the binary classification. So in the binary case, it's not super significant. That's because it's just a binary. So the information is contained in some kind of some of the parsers. So that sort of is more than enough. So we don't need extra fine parsers. In this case, we need extra fine parsers, and we are able to achieve a sort of decent improvement. So here we have what happens when we have these kinds of thresholds. So this is the baseline. So what happens when we sort of map, for the mapper training, we only use very good sort of words which have occurred in the training. That means it has occurred more than n times. Here we see a sort of a balance. It says that if it has occurred n number of times, but then we remap the words which have occurred less than n times, and then if we run the parser, then we get a significant boost, and that's what we see. So it seems like these kinds of mapping thresholds is sort of important, and we see the cases of overfitting which happens in the parser. So if you have words which occur less than n times, then it overfits and it's not able to get the best result. So here we describe the approach. So there was a KNN approach. This is the KNN approach. So what they're telling is, in one space, if n words are similar, and in the other space, the other n words are similar, let's have the same clusters. Let's have unknown words pushed to the similar kind of clusters. Those don't perform as well. We see that it doesn't perform, it performs even worse when we have completely out of domain data sets, because again, it's pushing from one particular space, and their clusters may not be similar because the task is completely different. So we see that the performance of our mapper is better. So what generally happens to get an intuition over here is, so in this particular case, attempted is a content word which is unknown. So it has not been seen in the parser. And this is an original sentence which is taken from one of these out-of-domain data sets. So here what happens if you have not, if you don't use the mapper and if you use a general parser, is this sort of gets it wrong. So this is wrong. So as soon as it gets this particular information is lost, and then one of the sort of arc is wrong, then all the other arcs sort of fail, and you have a completely failed parse. So in our case, since we are able to provide the information, just the lexical information, nothing else, we are able to get sort of a correct parse. But again, it always doesn't work, because in these parsers, they also use part-of-speech tags. So say our embedding, like try Google to find the title. So in this case, our embedding is sort of pushing Google to be a verb, while it has been, so the part-of-speech tag of Google has been correctly sort of, they got the part-of-speech tag correctly. So in this case, what is happening is the parser is not using lexical information, but uses just the part-of-speech information. And just by using that, it gets the correct parse. But in our case, since we are pushing it to the verb, we sort of get a wrong parse. So, so that means instead of doing just parsing, we should also do the part-of-speech tagging, and then maybe we'll be able to get close to that. So in general, why we did that is, this is a T-SNE sort of representation of the words. So I'm not sure if I can probably magnify it. So I don't know how that works. Okay. So this is the initial space. So in the initial space, the capitalized ones are the ones that we are interested in as of now. So the other ones actually are existing in the parser. Okay? So the capitalized ones are unknown words which are there in the initial space. So magnificent, marvelous, horrible, poor, etc. are existing. So this is how it exists in the initial space. So in the initial space, you can see that these words are clustered together. Some of these words are clustered together, etc. So I'll show you the parsing space, and if we just inject these embeddings into the parsing space, then what happens? So here I'm saying, okay, I'll just inject the words directly into the parser trained space. So now what happens is these two spaces are uncompatible. So these are completely differently clustered. These are differently clustered. All the other clusters, there is no mixing happening. So now the parser is unable to handle these words because they're in a different space. So when we map it, so this is what happens when we map it. So now these spaces are pushed towards each other. So magnificent, marvelous sort of mixes with all the other words which are close in the parsing space. Similarly, poor, ordinary, etc. mixes again to the space. Oops. Okay. So the general observations are sort of yeah.
Why the second and the third are not the same?
So the second and third. Yeah. So second is, so I have just learned the space. So the parser has trained and updated the embeddings.
Yeah, but I mean, you map all words in the third one, or only the unknowns?
Only the unknowns.
So all the others should be in the same place.
Yeah. So when you do t-SNE, the problem with t-SNE is it always doesn't.
It's a projection.
Yeah, it's just a projection. So the projection is not. The only thing you can say is the clustering in the projected space. So the observation is that we achieve significant improvements in dependency parsing, but there's a generic method which should be useful for other NLP tasks as well, where embeddings are used and where you're using some kind of neural network such that you are basically updating and these embeddings, and we get significant accuracy improvements. We also observe improvements over a downstream task that uses these kinds of things. So it states that this is really working. And I think our approach is pretty simple. It's effective and applicable to various other settings in general. And that's it, I think. So I'm sorry, I didn't repeat the questions that when Louis asked. Okay.
So compared to as we said, you got another option that is to froze the edits and not to adapt.
Yeah, that.
What's another layer?
Yeah. So one of the things, if you. Yeah. So one of the things about freezing the embeddings is that you're essentially ignoring the compositionality. So the embedding compositionality, say a word with another word, might give you some. So say I say Google with. If I say these two, then there is a composition between these two words. So you ignore these kinds of compositions. So the yeah.
They use the noun they use a common vector for a noun.
Yeah.
So instead of just frozen, so maybe of course it's better.
Yeah. So one of the reasons is compositionality. So there are papers in neural networks, theoretical neural networks, where they say that compositional information, like combination of different objects in the initial layer, can be captured only if you backpropagate to the final thing. So.
Another way, like is saying what the difference I see. One is our
Yeah.
Another is the measure problem. The measure, because in the first case you will use the same objective final parsing method.
Yeah.
Measure, but now here you're using the L1 and L2 measure.
That's one thing. The other thing is, so you know, normally in the initial layer you just concatenate the embeddings and then you pass it on, right? So when you concatenate, you're unable to sort of capture all kinds of information in all the dimensions, right? Unless you backpropagate. So theoretically, backpropagating can give you compositional informations in all dimensions, right? So that's one thing that you are unable to do if you freeze the embeddings. That's the first one. Say you project it, projection might be helpful, but again, there is a chance that, again, the problem of compositionality. You might project it to a nonlinear layer, maybe you'll get all the compositional information. But if you don't project to a nonlinear layer, then there is a chance that you might lose out, especially for structured prediction tasks, you might lose out on compositional information, which might affect your. So we also tried that, but we didn't get a significant improvement in that, and that's why we tried outside. But the outside thing is good because it can work for any case, so not just this case. So in the other case, you want that single layer specifically for each task, right? So then you have to make an architectural modification. So this is more generic in the sense there is no architectural modification. You can apply it for any case, and it should work.
You can apply to any task, but you need first the parsing task to have the embedded.
Yes, that's the only thing. So you need to have, so what I'm saying is architectural modifications is not needed. So if you have a model, then you can use it, get the embeddings, and then